Hi, this is Miss Boudreaux again, and we are going to talk about how the atomic model is changed by Bohr. And Bohr, we need to learn some things about light and waves and things like that before we can discuss him. So this first section, we are going to discuss how how wavelength, frequency, and speed of, of radiation come into play. We're also going to talk about the dual nature of light. So, you all know who this person is. Uh, Dumbledore from Harry Potter, and he has a famous quote there that says that happiness can be found even in the darkest of times if one only remembers to turn on the light. Since we're talking about light, I thought that would be an appropriate slide. So, light can be described as a wave. I don't think about it, but light travels across the room as a wave. We don't see the actual wave, but that's how it travels. So we have something called electromagnetic radiation. It's energy that shows the same behavior as a wave as it travels through space. And all the different forms of electromagnetic radiation form what we call the electromagnetic spectrum. So I jump ahead 2 slides, and here's one section of waves. This is what we call visible light. You might have learned it as the rainbow or Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. But when we're talking about the properties of light, we can discuss that it has a frequency and it has a wavelength. So the longest wavelength are the red lights. Things that are red have a long wavelength and they don't move quite as fast as the darker things like violet, which has a very high frequency and a very short wavelength. So going back to the previous slide, we can see that if we look at a whole number line here, this tiny little portion that's in blue, light blue, is the only portion of waves that we can see with the naked eye. So we can see visible light, but all of these other things on this long number line are waves that are in the air that we just cannot see with our eyes. So let's start at the right end. At the right end are the very, very long waves. Long waves as in 10,000 or 100,000 meters long. 100 meters would be approximately a football field. So 100,000 meters would be 1,000 football fields. Well, radio waves are often long waves. And there are certain types of radios called ham radios, and they use long waves. They can discuss and talk with people on the radio across the globe just by sending long radio waves and the radio wave landing in another country. And they can have conversations on these radios. Then there are radio waves like the ones we listen to in our car. If you have ever had your parents want to listen to WWL radio during the hurricane, that's because WWL radio is an AM radio station that has coverage about storms and things like that. So those radio waves are only about 100 to 1,000 meters long. Moving to the left, we can talk about the waves that come as television waves or FM radio waves. Like if you're listening to KQKI on the radio or another radio station, then you're going to be on the FM radio waves. Those waves in length from the top of one to the top of the next would be about a meter or 10 meters long. So they're getting shorter, you see? The next type of waves would be concerning your cell phones. Cell phone towers use microwaves. Also, of course, your microwave oven has microwaves. We don't see what's happening in the oven when it's cooking our food, but inside the oven, there are waves going through the oven, and the waves are hitting your food, and the moisture, the water in your food is being hit by the waves, and that's what heats it up. If you've ever noticed when you put something in a microwave, the plate inside the microwave that you put it on doesn't get hot where the food doesn't touch it, because the microwaves don't affect the plate, they only affect the water in the food. So microwaves. The next type of waves on the spectrum is IR waves, or infrared. Those are heat waves. If you ever heard of night vision goggles or IR goggles, infrared goggles, then those are looking for the heat of someone or some heat in a body that's alive. So infrared waves are getting smaller and smaller. Then we have visible light, 10 to the negative 6, 10 to the negative 7 meters. So a micrometer or less. The next type of light is UV light, ultraviolet light. UV light is the light that comes from the sun. And if you have a black light, if you've ever seen a black light, then those are UV lights. Those are dangerous for humans. That's why we use sunscreen, because we want to get UV protection. We want to get protected from the ultraviolet lights because it can cause skin cancer. It goes to skin. Then, if you've ever had a bone broken or you've ever had to have a chest x-ray, many people who are suffering from COVID-19 have to have x-rays of their chest to see if there's something in their lungs keeping them from breathing. X-rays are in the length of a nanometer, 10 to the minus 9. Even smaller than X-rays are something called gamma rays. And if you remember the Marvel comic, The Hulk, in the jingle about the Hulk in the song, it talks about that Doc Bruce Banner was pelted by gamma rays and turned into the Hulk. Gamma rays are picometers in length. They are so small they can go into your body, into the cells, into the DNA, and change your DNA. So gamma rays are very dangerous and often lead to cancer because they change our genetics. So this is the spectrum, the whole range of waves that are in our world, from long waves all the way to the smallest wavelengths being gamma rays. And again, the visible light is just one small section of that whole spectrum. Well, you've heard me use some funny terms, so let's define those. One of them is called the wavelength. And wavelength is the distance between the same point on two waves that are next to each other, two adjacent waves. We use wavelength as a symbol. Looks like an upside down Y, but it's called a lambda. It's a Greek letter in the alphabet. It corresponds to our letter L, and it's called lambda. And that's the symbol we use when we're talking about the length of a wave. Another symbol used in talking about light is the frequency, and that is a small v, sometimes written as a cursive V, and then it's actually supposed to be the Greek letter called nu. Frequency tells us how often something happens. In this case, it tells us how many waves pass a given point in a specific amount of time. In this case, 1 second. I'll try to make this easier to understand. How often do you see your grandparents? If your grandparents live in St. Mary Parish, or if your grandparents live in Louisiana, you might see them every day. You might see them every week. You might see them once a month. I'm a grandmother. My grandchildren live in another state, in Colorado. So I don't see my grandchildren more than maybe twice or 3 times a year. So the frequency of my visits is lower than possibly the frequency of your visit. So frequency just has to do with how often something happens over and over again. So we have these two quantities, wavelength and frequency, and they are mathematically related. There is an equation relating frequency and wavelength. Lambda remembers wavelength, the V is frequency. If we multiply those together, they're always equal to a constant. And it just so happens that that constant, C, is the speed of light, which is a number. It is 3.0 times 10 to the 8 meters per second. So anytime we have a wavelength and a frequency, if we multiply them together and have the correct units, we should get 3.0 times 10 to the 8 meters per second. Let's look at a picture describing wavelength. So wavelength and frequency. Wavelength is going to be the distance between 2 points on adjacent waves. So if I'm standing on a pier and I'm watching the waves come in, then if the tide is coming in or the waves are coming in slowly, I will see a very long wavelength, like in picture 1. The distance between the top of one wave and the top of the next one is great. So that would be a long wavelength. But the frequency of that splashing as it hit that pier would be very slow. So wavelength, if it's long, then frequency is small. Conversely, if we look at the second picture, the waves are coming in very quickly. The frequency of the waves hitting the pier is high. So the frequency is large, but the distance between waves is tiny. So they are inversely proportional. If one is high, the other is low. I'm going to stop right there.